Goals of the buffers lab include measuring the pH of several acid and base solutions, determining the effect dissolving a salt has on the pH of a water solution, plotting the pH of buffered and non-buffered solutions when adding acid or base, determining if dilution of a buffer solution has any effect on its pH, and preparing two buffers. Techniques include the use of a pH meter, measuring accurate volumes of acid and base solutions, and the preparation of a standard solution of a weak acid. Math skills needed for this experiment include calculations involving molar mass and solution volume to prepare a standard solution, use of the dilution equation, and predicting pH using the Henderson-Hasselbalch equation. The initial part of this experiment determines what, if anything, happens to the pH of water when adding a small amount of salt, such as sodium carbonate or ammonium nitrate. The question we must answer is the pH of this solution changed from a neutral value of pH equal to 7? Consider the salt sodium carbonate. This salt is soluble in water, and it dissolves to form two ions, the sodium cation and the carbonate anion. This equation is called the dissociation equation and simply shows the dissolving of the salt in water. The sodium ion is the conjugate of a strong base, so it will not affect the pH of water. There is no further reaction of this ion with water. Carbonate, however, will react with water by removing a proton, which increases the hydroxide concentration. CO3 2- is the conjugate of a weak acid. This results in a basic solution. The pH of this salt solution will therefore be greater than 7. Now let's consider another soluble salt, ammonium nitrate. The dissociation equation shows that this salt forms the ammonium cation and the nitrate anion when dissolved in water. This is the dissociation equation. Nitrate, or NO3-, is the conjugate of a strong acid, so there is no further reaction of the nitrate ion with water. Ammonium ion, or NH4+, is the conjugate of a weak base, so it can affect the pH. The ammonium ion will donate a proton, or H+, to water and form ammonia, NH3, and hydronium ion, H3O+, as shown in the hydrolysis equation. Since there is H3O+ formed, then this solution will be acidic with a pH less than 7. In this lab, you will also measure the pH of strong and weak acids. Consider the dissolving of the strong acid hydrochloric acid, HCl, in water. The products formed are hydronium ion and chloride ion. The weak acid nitrous acid also forms the hydronium ion in water and its conjugate base, NO2-. So, what's the difference between these two acids? The reaction arrows are used to indicate the difference. An arrow which points to the right indicates that the reaction proceeds entirely to the right. That is, the reactants are completely converted into products, at least until the reactant present in the smaller mole quantity is used up. The double arrow, on the other hand, indicates that both reactants and products are present, so that not all of the weak acid reacts to form hydronium ion. The following bar graphs indicate this difference. Although 100% of HCl ionizes, only 6.7% of nitrous acid ionizes. This indicates that there is still a large quantity of HNO2 present when compared to the amounts of products formed for this weak acid. If the concentration of both acids is initially 0.1 molar, then the concentration of H3O+ formed by HCl is 0.1 molar, and this concentration for HNO2 is only 6.71 times 10 to the minus 3 molar. Converting these concentrations into pH gives a value of 1 for HCl and 2.17 for HNO2. The lower pH clearly indicates the more acidic solution. This lab also examines buffers. A buffer is a solution that contains either a weak acid and its conjugate base, or a weak base and its conjugate acid. This unique composition of both an acid and a base allows a buffer to resist changes to its pH. Those instances where a buffer resists a change in its pH are when it is diluted, when a small amount of acid is added, and when a small amount of base is added. Consider the acetic acid acetate buffer, which contains the weak acid acetic acid and the conjugate base acetate, which is contributed by the salt sodium acetate. If a base, such as sodium hydroxide, were added to this buffer, the hydroxide ion would react with the acid component of the buffer, which is acetic acid, to form acetate anion and water. If instead an acid were added, such as hydrochloric acid, the hydronium ion H3O+ would react with the base component of the buffer, acetate anion, to form acetic acid and water. Note that a buffer contains the components necessary to react with either an acid or base. The Henderson-Hasselbalch equation relates the resulting pH of a buffer to the pKa, which is the weak acid's equilibrium constant in water, and the concentrations of both the conjugate base and weak acid. Note that by knowing any three of these quantities, the fourth one can be determined. A special case occurs when the concentrations of the conjugate base and the weak acid are the same. This equation simplifies. Since the log of 1 is 0, then the pH is equal to the pKa. Consider the reaction resulting from the addition of 0.1 molar sodium hydroxide to 17.5 ml of 0.1 molar acetic acid. The following curve shows what happens to the concentrations of acetic acid and acetate ion during the progression of this reaction. As base is continually added, the concentration of acetic acid goes down. At the same time, the concentration of acetate ion is increasing. At that point, where the reaction is 50% complete, the concentration of acetic acid that is left equals the concentration of the acetate ion that has been formed. By continuing to add sodium hydroxide, a point is eventually reached where all of the acetic acid is converted to acetate ion. A titration curve can be used to monitor the same reaction, where the pH is monitored as base is added. The endpoint indicates the volume of sodium hydroxide needed to completely react with the acetic acid. The region on the titration curve around the point where the reaction is 50% complete, that is, where the concentration of acetic acid equals the concentration of acetate, is where the greatest buffering capacity is on this curve. This halfway point is also where, according to the Henderson-Hasselbalch equation, the pH equals the pKa. Due to the limited number of pH meters, this experiment is completed in groups of 2. When dissolving in hydrated salt which contains water in the formula, such as sodium acetate trihydrate, the products in the dissociation equation include just the aquated cation and anion. The waters of hydration just become part of the water in the resulting solution. In the case of copper sulfate pentahydrate, water molecules are actually bound to the copper ion to form a copper complex when the copper sulfate pentahydrate dissolves. And these 4 water molecules must be shown in this resulting copper complex to account for the non-neutral solution that is formed. The TA has already calibrated the pH meters, so they are ready to be used. Make sure to rinse the electrode with deionized water when changing solutions. Unless rinsed, small amounts of one test solution can be transferred to another, contaminating it and affecting the measured pH. In the last part of this lab, you will prepare 2 buffers. When you make a buffer of pH 3.85, first calculate how you would do this, then have your TA check your calculations before preparing the buffer. For the buffer with pH 2.9, you prepare it experimentally. Add to the weak acid small measured volumes of sodium hydroxide solution until the appropriate pH is reached. Make sure to record the total volume of NaOH added.